responsibility to go back to your calculus, with both everyone you used, and review partial derivatives. Okay, we're only going to be using the most basic definition, and I'll try to quickly cover all that, right here. Okay, so the idea now is we have a function u, which is a function of two independent variables, x and y. Okay, and that can represent anything. Maybe it's an electrostatic field in the xy plane, or maybe you have a plate. Okay, and u of xy is the temperature at a point xy. Okay, and the idea now is that there's two independent variables, x and y. And you're probably thinking, wait, this is ordinary differential equations, and we thought that when you have two or more independent variables, it becomes a partial differential equation. But actually, there's some simple techniques for integrating first-order partials, which I'll go over, which can be used to advantage on so-called what's called exact equations. Okay. Before we go on, I'm just going to remind you of these are just basic definitions. Okay. So if I have a u that's a function of x and y, what's partial u partial x? It's just what it is basically is that it's the derivative like you have in the normal case where y equals a function of x, but you keep one of the variables fixed and you only vary one. So partial u partial x, what it means is take the rate of change of u with respect to x, keeping y fixed. So it will be the limit as delta x approaches 0 of u of x plus delta x y, right, minus u of x y divided by delta x. And notice what happens. I went from the point x, y, and I only incremented the independent variable x. Okay? So I went from x, y to x plus delta x, y. So the way you do these partials is you just differentiate respect to x, making believe that y is fixed, even though y is a variable. Because that's the definition of a partial derivative. And of course, the partial u partial y has an analogous definition. But there, we're changing the y variables. That's the limit as delta y approaches 0 of u of x, y plus delta y, right? Minus u of x, y, and now, of course, we're going by delta y. That's just your basic definition of the two partial derivatives. Okay, so let's just do an example over here. Suppose u is x squared, sorry, I'm just making this up, y cubed plus the sine of xy. Okay? Okay, and I want to calculate partial u partial x. Okay? Like I said, this should all be review. Okay? If it's not, you got to review it on your own. Well, I go through there and I just differentiate respect to x, making believe y is fixed. Well, derivative of x squared is 2x. I just make believe that the y is fixed, so it's y cubed. And now, of course, we use the chain rule. Derivative of the sine is the cosine of xy. And what's the partial respect to x of xy? It's just y. Okay? So that's partial u, partial x. Okay? And what would partial u, partial y be? Well, go back now, make believe x is fixed. The derivative of y cubed is 3y squared. So I get 3x squared y squared plus, using the chain rule again, the derivative of the sine is the cosine of xy. And the derivative of the argument with respect to y is then x. So notice the difference between here and here. Okay? This should all be, very familiar to you. It's way worse. Okay. Now, one thing which is going to be critical, okay, and what I've seen, many times is that there's a big difference between partial u partial x and what people will write as du dx, normal derivative. Okay? For example, if y was implicitly a function of x, then you could plug in for y in terms of x, u would be a function of a single variable x, and then the normal derivative du dx would make sense. Okay? So don't be sloppy and write this thing if you mean this or vice versa. They're two different things. And where it's critical is when you do integration. And let me just show you that. Okay? The type of things we're going to have, the type of differential equations we have to integrate, PDEs we're going to have to integrate, are things, simple things like this. Okay? Where I want to go back, say, from here to here. Okay? But instead of doing that, because we know the answer, let's find the integral of u with respect to x. Okay? Making believe y is fixed. Okay? And again, you have to be careful. Okay? Because if y was a function of x, you'd have to plug that in first before you do the integration. But many times we'll have an equation like this, and we want to go backward. Okay? But let's just do this now. Okay? What would be the integral of u dx? And by this I mean, that you're integrating with respect to x, making believe y is fixed. Okay? Well, you keep the y cubed, right? okay? And the integral of x squared dx is x cubed over 3, right? And then you have to be careful now, the integral is sine. Let's see now, we'll get a minus cosine of xy. And what do we need over there, right? If I differentiate with respect to x, okay, if I differentiate with respect to x, I would then get a y, so I gotta divide, I guess I divide 1 over y. Plus, this is the important part over here. Let me just read this again, okay? So if I want the integral of u with respect to x, and I believe y is fixed, I get x squared, that becomes y to the 4th over 4. That's the integral of y cubed. Okay, minus cosine of xy. And what factor do I need? If I took the partial with respect to, I'm integrating with respect to y, I'm so sorry. Okay. I want to go with respect to x. So it's x cubed over 3, y cubed, right? Plus, it's a minus because it's a cosine. Cosine xy, I need a factor over here, right? Because I did du dx, I would get sine of xy, then I get a y, so I get a 1 over y. Here's the important part, plus an arbitrary function of x, where phi of x equals arbitrary function of x. Now, why do I get that? Okay, if I had an ordinary derivative, for example, if I had, suppose u was just x squared, right? Just a function of a single variable. Then if I did the integral of u dx, okay, what would I get? I get x cubed over 3 plus an arbitrary constant, right? But now you have to realize that I'm integrating with respect to x, making believe y is fixed, okay? And best way to check this is go back over here and do the derivative with respect to x, okay? See what happens? You get 3x squared over 3, which is x squared y cubed. That's the first term. And if I differentiate this guy with respect to x, I get a plus sign of xy times y, okay? Which of course cancels there. And what's the derivative of phi of x? What's the partial? Oh, I'm so sorry. It's phi of y, arbitrary function of y, right? Okay. If I do basically, if I differentiate phi of y with respect to x, I get what? 0, okay? Just remember, d by dx, y held fixed. So the important thing is that when you integrate a first order partial differential equation, instead of picking up an arbitrary constant, you pick up an arbitrary function of the other variable, okay? And just to do the other one, suppose I want to do the integral of u with respect to y. Again, x and y is independent variables. Now I do my integral with respect to y, I make believe x is fixed, so that x squared stays the same. Then I get y to the 4th over 4th, right? And then I get a minus cosine of xy, and then I get 1 over x, right? Plus now an arbitrary function of x. And let's just check that. Let's take the partial derivative of this with respect to y. So I have x squared times y cubed, yeah, that's the first term. If I differentiate this guy with respect to y, the 1 over x stays there, right? I get a plus sign of xy times x, which is a sine xy. What happens to this guy? It goes to 0, because I'm taking the partial derivative with respect to y of a function of x only, okay? So this is the thing you have to get used to, that when you have these first order, we're going to get equations like this, and you have to remember to add on not an arbitrary constant, but a function of the independent variable, an arbitrary function, okay? That's really all we need to know about integrating partial differential equations. Okay. Okay, and now, again, so that may be a little bit new because, you know, usually you don't do that in the first year calculus course. But the idea is simple, right? You just, if you're integrating partial, let's call it partial integration with respect to x. You do it just like you integrate with respect to x normally, but you have to remember to put in that arbitrary function of y, and vice versa if you do the other derivative. Okay. Now, suppose, again, I basically I'm going to go from 2 points. I'm going to go from xy to a neighboring point, x plus delta x, y plus delta y. And like before, I've got that function u, which is a function of the 2 independent variables x and y. And I want to know the increment in u due to the change going from here to here. So if U was the temperature, what's the temperature change in going from here to here? Okay? Well, we'll define that to be delta U, and by definition, I'll put it like that. It's U of x plus delta x, y plus delta y, right? Minus U of x, y. That's just the definition. The change in the temperature as we go from x, y to x plus delta x, y plus delta y. Now the idea is we want to relate that to the partial derivatives. But the problem over here is that you're changing both variables, both x and y. So there's a little trick here. You remember from calculus, we're going to just change one at a time, okay, and write it equivalently. Let's write it as u plus x plus delta x, y plus delta y, okay? And then, if I want to get an x partial, I guess I do minus u of x, y plus delta y, right? So now I'm just changing x, but I just can't have to add it back because I just can't change it arbitrarily. U of x, y plus delta y minus u of x, y. So the trick here is I subtracted and I added the same thing, u of x, y plus delta y. And the reason for that is because, just not, you should understand why it's going on, because then you see when I look at the first two terms, I'm keeping the y variable fixed at y plus delta y, and I'm going changing x from x to x plus delta x. And in the second term, I'm going from x, y, and keeping x fixed, going from y, y plus delta y. Okay? So now what happens is delta u equals, let's write this as u of x plus delta x, comma, y plus delta y, minus u of x, y. Let's divide that by delta x, because you just can't change it. You have to multiply by delta x, right? Otherwise I change it. So there's the first two terms. And for the last two terms, let me write that as u of x, y plus delta y, minus u of x, y. And what changed over here, it was delta y times delta y. Seems kind of silly, but you'll see in the reason why I'm doing that. Okay. Now, I erased it, but you recall the definition of partial u, partial x, right? It was u of x plus delta x, y minus u of x, y over delta x. Take the limit as delta x goes to 0. And here's what I'm going to do over here now. Okay? I can write this delta u as, imagine now that I replace the expression u of x plus delta x, y plus delta y minus u of x, y over delta x with partial u, partial x, evaluated at x, y. Well, I can't do that because that's not what I have. And then I have an error. I'll call that epsilon 1 times delta x. So in words, what's epsilon 1? Epsilon 1 is just basically the error replacing this guy by its derivative. And it's obvious that epsilon 1 goes to 0 as delta x and delta y go to 0. Right? You need both, because you want this to go to u of x plus delta x minus u of x, y over delta x, and also delta x goes to 0. So we can write down over here, epsilon 1 goes to 0 as delta x and delta y go to 0. Okay? And what we're going to do over here, okay? This one is less complicated, right? Right? This is exactly the setup for partial u, partial y. If you took the limit as delta y goes to 0. So let's replace that guy by partial u, partial y at the point x, y, plus another error, epsilon 2 times delta y. And we see that epsilon 2 will go to 0 as what? Just delta y goes to 0. Okay, so it's interesting over here that this error, epsilon 2, will go to 0 as delta y goes to 0, because it's got x and x over there. But to get this error to go to 0, we need both delta x and delta y going to 0. Okay? And now we're just going to rearrange this, and you'll see things that you've seen before. So you got partial u, partial x. I'll leave off the evaluated xy times delta x. Okay? Then from there, I pick up a partial u, partial y at xy times delta y. Right? And then I have these two error terms, epsilon 1 delta x plus epsilon 2 delta y. Now, think of delta x and delta y as small quantities, okay? Epsilon 1, epsilon 2 go to 0 as delta x and delta y go to 0. So these are like second order infinitesimals, as they would say. And this part over here is called the principal part of delta u, and that's what you know is du. okay? The total differential, okay? And you would need this form basically when you develop the chain rule, right? Suppose like the temperature was a function of x and y, and there's a trajectory you're following. So x is a function of t, is y is a function of t. Then u, the temperature, will be a function of t, and then you have the familiar chain rule, partial u, partial x, dx dt, plus partial u, partial y, dy dt. Okay? So, and you're probably wondering, what does this have to do with integrating ordinary differential equations? And you'll see this in a second. So what we come out over here basically is kind of the differential of u. It's just a definition now. It's partial u, partial x, dx. Of course, for infinitesimals, delta x is dx, right? And partial u, partial y, dy. So this differential of u basically is what's called the principal part of delta u. So it says that basically when you go between 2 points, x, y, and x plus delta x, y plus delta y, the change in u is basically the differential of u plus a correction term. But that correction term goes to 0 very rapidly as delta x and delta y goes to 0. Okay, this all should be reviewed here. Okay. So, how does this relate to our next topic? Okay, we're going to basically now look at first order, what's called exact ordinary differential equation. Okay? We'll define exactly what we mean by exact and how you solve it. Okay? There are a lot of equations that occur that are very nonlinear, but actually can be integrated because they fall in this category of exact. Okay, so the equation we're going to be looking at for the rest of today is the first order, and let's write it as m of xy dx plus n of xy dy. This is the notation the book uses, is equal to 0. Obviously, that's what? dy dx is some messy function of x and y. Okay? So any differential equation can be put in that form. Okay? And the question is, under what conditions can we integrate this? Okay? Okay? And this is where you have to be careful. We're going to do both necessary and sufficient conditions. Let's do the easy part first. Okay? Suppose m dx plus n dy, which is I just wrote, was equal to the differential of u. Okay? Then we say that basically that the expression is exact.